Hello, my name is Ananta Satriadi. I'm currently a research fellow at the Embodied Visualization Group, Monash University, Australia. At the time of the research, I was a postdoc at the Wearable Computer Lab, the University of South Australia. All co-authors of this work were a team from the University of South Australia. This paper was published and presented at ISMAR 2022 in Singapore, and it's a pleasure to have a chance to present this work again to the PhYS community at PhYS 2023. The paper is looking at how to present multivariate data around physical scale models in augmented reality. The driving scenario of our investigation had been brought to us by an industry partner. We had been working closely with our partner in the maritime domain to explore how AR solutions could support problem solving and sense making of data on shipbuilding subfloors. In these settings, complex relationships existed between the physical machines and their historical multivariate data. The existing data visualization workflow at the time primarily emphasized data representations without considering the physical and spatial context of the subfloor. Our partner mentioned that it is crucial to gain a comprehensive view of the entire subfloor and to comprehend the intricate relationships between the complex data and the specific machine to which the data pertains. So we conducted research around the topic and drew inspirations from the concept of situated and embedded data representations. These concepts proposed that bringing visualization closer to their physical reference could enhance the user's understanding of the data. And in this scenario, the machines on the subfloor are physical reference of the abstract data. Typically, situated visualization involves immersing the users and the visualization in the actual subfloor environment. However, due to various limitations such as restricted access to the subfloor, we opt to substitute the actual physical machines with scaled-down representations, essentially using physical scale models. A few prior studies have explored the utilizations of physical scale models for data visualization in AR. For instance, among several existing examples, the uplift system by Ens et al. Places visual marks representing spatiotemporal attributes on top of the building scale models. While these studies have demonstrated the potential of such systems for representing complex data, there is still limited explorations of techniques for visualizing multivariate data with multiple charts per scale model. We use augmented reality to display various data attributes using familiar representations like bar charts, scatter plots, and line charts, and strategically position them near the scale models as physical reference points. Illustrated by this figure is one of the 6 techniques that we explored. We all know that immersive environments such as AR provide more display space than 2D desktop screens for data visualizations. However, the display space for augmented scale models has notable constraints if we take into account the placement of AR charts and the scale model, chart readability, and the occlusions between the charts. This work then focuses on the following questions. How can we effectively use the 3D space around scale model to present multivariate charts? We consider 2 factors, namely charts layout and view arrangements. From these 2 factors, we came up with 6 techniques and we evaluate them in the user study. Our paper presents 3 key points. We present augmented scale model visualization techniques that enable presentations of multivariate data and their physical reference representations. We present design considerations for presenting multivariate charts with augmented scale models that look at 2 main factors, charts layout and view arrangement. Lastly, we present empirical findings and design implications from a control user study evaluating these factors. In the upcoming slides, I will guide you through the 2 key design factors we have taken into account, and I will provide a concise overview of the results of our user study. So the first factor revolves around the chart's layout, influencing how multiple charts are presented in conjunction with each scale model. Our investigation delved into 2 widely recognized layouts, the dashboard layout and the slides layout. The dashboard layout arranges all charts in the grid-like format, facilitating the simultaneous observations of multiple charts. However, as evident from the video, this technique compromises the individual chart size, which might impact overall readability. The slides layout, on the other hand, displays only 1 chart at a time but offers a larger chart size, making it advantageous for showcasing intricate details and incorporating additional information like annotations. However, it places a substantial reliance on user interaction to navigate between charts. The second factor to consider is the view arrangements, which dictates how charts views are positioned in the spatial context surrounding the scale models. One crucial requirement we aimed to fulfill was to minimize the occlusions among chart views. To satisfy these conditions, we introduced three distinct view arrangements. The on-virtual board arrangement offers an orthogonal grid layout for facilitating charts comparison tasks. In this clip, we have the dashboard layout with the on-virtual board arrangement. While such an arrangement might be good for tasks such as scanning information, it may not seamlessly integrate with the associated scale models. This video clip and the following clips were taken from HoloLens in our user study setup. Here we're looking at the slides layout featuring on-virtual board view arrangement. We notice the presence of the next and previous buttons which facilitate navigation between individual chart views. In the center, there's a sync button that allows participants to synchronize all the slides across all models. The on-scale view arrangement spreads out the view horizontally, aligning them with the user's horizontal visual angle and billboarding them toward the user for an optimized viewing experience. This is the dashboard layout with on-scale models arrangements. For these arrangements, we use a simple algorithm that takes each view's angular size and arrange the views in a non-overlapping manner. In our study, this algorithm was only triggered once at the beginning of the on-scale model's conditions. This is the slides layout with on-scale model view arrangement. The on-table arrangement situates the views on the table surface encircling the boundary of the scale models. This is the dashboard layout with on-table view arrangements. As we can see here, this approach closely resembles tabletop display visualizations and top-down projected augmented reality. So this is the slides layout with on-table view arrangement. Both on-scale models and on-table arrangements maintain the integrations between charts and models, but we can see here that their views are not arranged as closely as those on virtual board. In the next slides, we will see several key findings from our user study. The analysis of response time shows that participants were significantly faster when charts were placed on scale model than on table and on virtual board, both by 20%. Subjective measures also suggested that on-scale models integrated charts with their models better than on virtual board, and that comparing charts across model was easier than on-table view arrangement. Results of the response times analysis show that performing complex comparison tasks that involve multiple charts and models with slides layout could take 37 to 55% significantly more time than with dashboard layout. Despite that, for simple comparison tasks, both layouts perform equally well. This results indicates that slides performance is highly sensitive to task complexity, while this effect was not found on the dashboard layout, whose performance remains steady in all tested task types, as we can see on this graph. We also found that subjective measures in favor of dashboard. As we can see here, the slides layout received significantly worse measurement values than dashboard layout in preference, mental effort, physical exertions, confidence, ease of use, and support for comparison tasks. Reading small charts on dashboard layout might be a fair compromise over the navigation complexity of slides layout. This is supported by the absence of significant differences in ease of reading subjective measures for both layouts. The results show that charts layout and view arrangement factors do not significantly affect the task error. However, we did find error differences among task difficulties. So the on-table view arrangement might be a good fit for tasks that require chart model integrations, since the leader lines that connect the charts and scale models are clearly visible and potentially free of crossings. However, it requires participants to work more than with on-virtual board view arrangement, making it not a favorable option for comparing charts across models. The virtual boards facilitate charts comparisons across scale models because it aligns charts on the grid and requires less working than on-table view arrangements, but relating the charts with their models was found to be a bit problematic. Our study showed that on-table arrangement might be a good compromise between the other types of view arrangements with minimal working and good support for chart comparisons across scale models. With these slides, I would like to briefly acknowledge external support. In summary, we explored the techniques to present multiple charts around physical scale models in augmented reality workspace. Our findings favor charts layout that support simultaneous charts viewing combined with the type of view arrangement that have high integrations between charts and scale models and great support for chart comparison across scale models. Thanks for the opportunity and please refer to our paper for more details.